So today, today we have a visitor from the Dark Institute at the University of Copenhagen, Nikki Arendse, who does a PhD there, and she will tell us about cosmic dissonance. And I want to remind everyone that during the talk, questions are not allowed, but we have plenty of time after the talk. So Nikki, go ahead.
Okay, thanks. Yeah, and thank you so much for the organizers for inviting me to talk here. And the work I will be talking about today is carried out with my supervisors Radek Wojtek and Adriano Agnello. And it's called Cosmic Dissonance, and it focuses on the Hubble constant, so the present-day expansion rate of the universe, which is a really important parameter if we want to understand our universe, because we need it to calibrate the distance scale and also to determine the age of the universe and the expansion rate in the past, the present, and the future. But we all know that when it comes to the Hubble constant, we have a problem. And sort of recapping, there are two different ways how we can measure the Hubble constant. The first one is using local data. So this is similar to how Edwin Hubble and Lemaitre did it back in their day, where you look at astronomical objects and you determine their distance and redshift. And then you can use this to get an estimate of the Hubble constant, which, depending on which data set you use, you get sort of a high estimate, around 73. The second way is using the CMB, and by looking at the peaks in the power spectrum, you can determine cosmological parameters at recombination, and then use a cosmological model to extrapolate them forward to redshift 0 to get the Hubble constant. And this method with Planck gives a low value of the Hubble constant, around 67. And the difference between these two measurements is often referred to as the Hubble tension. And it's one of the biggest problems in current day cosmology, because of course, this difference might be caused by some sort of hidden systematics in one of the two approaches, but it also questions our understanding of the universe, because the CMB method, like I said, in order to extrapolate these cosmological parameters, it needs to use a cosmological model. And so it uses the lambda CDM model. And this means that if something might be slightly off with lambda CDM, this could explain why we get a different value from the CMB. So that's a bit of background. And then today in my talk, firstly, I will emphasize that the Hubble tension is actually not just about H0. And then I'll discuss the important questions, whether modifications of lambda CDM can alleviate the tension. And finally, I'll also discuss some promising upcoming data sets. And I'll give a short sneak peek into some of my current work, where we're using gravitationally lensed supernovae to predict the Hubble constant. So like I said, it's actually not just about H0. And another important cosmological parameter that I would like to focus on in my talk is the sound horizon. So this is a distance scale in the early universe that originates because the baryons and photons are trapped together in this photon-baryon plasma, which means that if you have an overdensity, then gravitationally matter is attracted towards it, but there's also this photon pressure directed outwards. And these counteracting forces result in oscillations, quite similar to sound waves. So these oscillations travel outwards, and then when two meet each other, they compress and form a region with a higher density. And this process continues to unfold when the universe is cooling down until it becomes transparent enough and the photons and baryons decouple. And at this moment, the patterns that have been created are frozen in place. And the radius of these sound waves at recombination is the sound horizon. And so in these regions, you have a slightly higher density. So it also means that when the universe develops, there are more galaxies and clusters that are being formed in these shells, which we can still observe today around us if we look at the clustering of galaxies, the baryon acoustic oscillations, which you can see an artistic impression over here. And these baryon acoustic oscillations don't just give us information about the sound horizon, but also about the Hubble constant. Because if we focus on one BAO signature, like here, it could either be created by a short sound horizon in combination with a high expansion rate, or by a high sound horizon and a low expansion rate, so a low Hubble constant. And in this way, BAO constrains the product of H0 and RS. So this means that these parameters are very degenerate with each other. And here you can see the H0 RS diagram, where this yellow banana shape is everything that BAO constrains. And this is a good way to visualize the tension problem, because if you consider Planck, then they measure a high sound horizon and a low Hubble constant, while local measurements get a low sound horizon and a high Hubble constant. So this information that BAO gives us to link these parameters together is very valuable and should definitely be taken into account. Okay, so first to get a bit of an indication of the tension problem, we did a local determination of the sound horizon and the Hubble constant. So like I said, this is similar to the graph that Edwin Hubble made all those years ago. But now we have, of course, much more data points also extending much further out. And this means that it's not a linear relation anymore, but it becomes more difficult to develop an expansion history that can fit through all these data points. And there's, of course, one way that we can do it quite well, which is using lambda CDM. But because we are still speculating about some slight changes to lambda CDM, and the problem with the Hubble tension is an important one, we wouldn't really want our estimates of such important cosmological parameters to depend on a model that we're not 100% sure of. So for that reason, we also looked into some cosmology independent ways to fit these data points. And I'll shortly highlight one of these here. So this goal of describing the universe without adopting any cosmological model is sometimes referred to as cosmography. And as you can imagine, it's quite challenging to do this. So one of the ways is by using Taylor expansions. So usually in lambda CDM, when you describe the evolution of the Hubble parameter with redshift, then you use the Friedmann equations. But these equations have quite a lot of assumptions. So they assume that general relativity is true. And they also assume that the universe consists of several components like dark matter and dark energy, and that we know exactly how these components evolve over redshift. So instead of using this one, you can also just use the most simple formula that you can think of, which is a Taylor expansion around redshift 0. And so here the coefficients of these polynomials refer to the derivatives of the Hubble parameter at redshift 0. And just to give a bit more physical intuition to these components. So the Hubble constant is the expansion rate of the universe. And then we have the first derivative, which is the acceleration of the expansion. And then the second one relates to the change in the acceleration. And then you can use this formula to fit all your data points with Markov chain Monte Carlo. But like I said, this is the most simple way to do this. And it's arguably not the best one. So in our work, we selected 3 different Taylor expansions. And then we also used lambda CDM as model 4 as a reference. So some variations of these Taylor expansion are, for example, that you can expand a different quantity. So instead of the Hubble parameter, you can expand the luminosity distance or co-moving distance, because these usually have shapes that are more similar to the function that you're making. And then also, instead of expanding redshift, you can expand in a function of redshift, like log 1 plus z. And this allows you to have a wider range where this Taylor expansion is valid. And we also performed some tests for all these models. So one important thing is that if lambda CDM is the underlying cosmological model, then these models should be able to recover lambda CDM, which is what we tested here. And we required them to have an accuracy within 2%, which corresponds to the precision of our data, of our results. So this also determines then where you have to truncate these polynomials, because if you include higher orders, then you will get more accuracy, but also have larger uncertainties. And yeah, so this is one way of doing cosmography. There's also some other approaches using machine learning, for example, like Gaussian processes, that is also just taking into account the data points and then fitting a function through it, also returning uncertainties. So these are also promising methods. And the idea is really that if we go to the future, we get more reliable data points. So we have to rely on less assumptions to describe the expansion history. But of course, this means that the expansion history is only based on the data points. So it's important to take a look at these and make sure that, that they're obtained in the correct way. So for our project, firstly, for relative distances, we used type 1a supernovae from Pantheon, and also BAO measurements which introduce the sound horizon as a free parameter. And here you can see the distribution of these measurements over redshifts. But of course, these are only relative distances, so we still need to calibrate them. And usually this calibration is done either with Cepheids or stars at the tip of the red giant branch or surface brightness fluctuations. But the downside of these methods is that they can only be measured at relatively low redshifts. So it might be a bit risky to then extrapolate this calibration to the higher redshift data points. So this is why we also used 6 gravitationally lensed quasars. And here the Holy Cow collaboration have determined very accurate distances to these quasars. Just to get an idea of how this works, this is the setup of these quasar systems, where we have an observer and then a massive lens galaxy and a quasar behind it. And these quasars are usually quite distant, so maybe we would not be able to see it without the lens galaxy. But now the lens, the light of the quasar is being bent by the gravitational potential of the lens galaxy and also magnified. And this results in 2 images of the same object in this case. And the quasar also has slight variations in its brightness over time. And these variations will arrive at different moments at the images because the light is traveling a different path, and it's also affected by this potential in a different way. And then with extensive monitoring campaigns, we can actually observe these quasars for very long time spans, like sometimes almost 10 years. And then we can measure the difference in the arrival time of the images. So this allows us to get an estimate of this time delay, of the time delay, which in turn depends on the gravitational potential of the lens galaxy and also of the ratio of distances between the observer lens and the source, which is the time delay distance. So this means that if we measure the time delay and we also have a model for the lens potential, this allows us to get the time delay distance, which in turn scales inversely with the Hubble constant. So going back to our data points and how they're distributed over redshift, if we add these calibrations of the gravitationally lensed quasars, then you can see that they calibrate the data up to much higher redshifts. So this all sounds pretty amazing, but using quasars for cosmology is not without any challenges. So one major challenge is the Masshead degeneracy, which means that if you have a lens system and you scale everything up or down, then the time delays will be affected, but the imaging data will remain the same. And the only thing that you can use to really break this degeneracy is some information regarding the true size of the system. So for example, velocity dispersion of the lens galaxy. So this means that if we only have imaging data, then this is not really enough to distinguish between different mass profiles. And as you can see here, this also translates into the time delay distance, which means that there's this degeneracy between the lens mass model and the final estimate of the Hubble constant. Now for Holy Cow, how they sort of broke this degeneracy is by having some assumptions about the mass profile. So they assumed either a power law or a stars plus NFW profile. And in this way, you can break this degeneracy, and then they got an estimate of 73 for the Hubble constant, with pretty low uncertainties. But there's also been a different approach now by TD Cosmo, which performed a new analysis where they relaxed these assumptions on the mass profile, and instead they include a different data set from, these are not quasars that are lensed, but galaxies. So they don't have time delay measurements, but they do have velocity dispersion. So if you combine these two together, then this gives you a different value for the Hubble constant, which is 67.4. So exactly consistent with Planck, but you see that the uncertainties are quite a lot higher. But of course, this also has some hidden assumptions, which is that the lensed quasars and the lensed galaxies are drawn from the same parent population. So it's difficult to say which of these approaches is better, but it does mean that it's not true anymore that all the local data sets give a high value of the Hubble constant. And another example of this, this is something that just came out yesterday, actually. It's pretty interesting. So here in this paper, they took another look at the Cepheid color calibration, because SHUS assumes a universal color luminosity relation for all the galaxies where the Cepheids are in. But in this paper, they derived it separately for each galaxy. And what turns out actually is that for most of the galaxies, this color relation is lower than the one in the Milky Way, which also leads to a lower value of the Hubble constant. And then depending on how you distinguish between intrinsic color and extinction, you get an estimate of around 72 or 67. So again, consistent with Planck. So I think this is really extremely interesting. And although it doesn't necessarily mean that this is the complete solution to the Hubble tension, it does mean that we have to take these uncertainties of SHUS with a grain of salt, because effects like this really introduce some uncertainty. And then using all these data sets, let's move on to the results that we get. So initially we just used supernovae and BAO with a calibration of SHUS and Holy Cow. And here you can see the 1 sigma contours. So when we compare these to the measurements by Planck, then you really get this familiar picture of a really strong tension between the local and the CMB data points. But like I said before, this is only part of the measurements. And if you include different local measurements like surface brightness fluctuations, or the TD Cosmo results, which have also a lower H0, or the TRGB, then you see that this tension is not so clear-cut anymore as it maybe used to be. And it's really only when you consider SHUS and Holy Cow together that you get this strong 5 sigma tension with the CMB. But nevertheless, these results are still important, so it is still a problem. And therefore, there are still many papers coming out with proposed solutions to the Hubble tension. And for this, it's good to keep in mind that for the local data, we can determine the measurements in a cosmology-independent way. But for the CMB measurements, because we need to extrapolate the parameters to redshift 0, we need to use a cosmological model. So lambda CDM is always used. And then the question arises, of course, are there any changes that we can make to lambda CDM that can shift these contours of the CMB closer to the local ones and thereby reconcile the tension? Well, that's the question we addressed. And so many different models have been proposed in the literature, but we just focused on 4 of these. But they're actually examples of 2 categories of models that most models fall into, which is they can either change the early physics before recombination, or they change the late physics after recombination. So first, let's have a look at how you determine the Hubble constant from the CMB. So for the physical size of the sound horizon, we know the sound speed in the early universe, because this depends on the density of the baryons and photons. And we also know the time that has passed between the Big Bang and recombination. So then we can calculate what the maximum distance is that the sound waves could have traveled, which corresponds to the sound horizon. And then for the angular size of the sound horizon, you can look at the power spectrum of the CMB, where the position of the first peak corresponds to the first compression of the waves. So then combining this physical and angular size of the sound horizon, this gives us an angular diameter distance from us to the CMB. And using a cosmological model, we can convert this distance into a value of the Hubble constant. So now in these modifications, what changes is that in the early universe, there's this extra component that contributes to the energy density. So for example, this can be early dark energy or extra relativistic particles. And they all have in common that they increase the expansion rate in the early universe, which then shortens the time between the Big Bang and the recombination. So it also shortens the distance that the sound waves could have traveled. So we get a shorter sound horizon. And because we still observe the same angular size from the power spectrum, this means that we have a shorter distance, which corresponds to a higher H0. Okay, then for the second class of models, which changes the late physics. So here again, we have this sort of standard scenario where this is a visualization of expanding space according to lambda CDM from the CMB to the current time. And in these class of models, nothing changes before recombination, but afterwards there's this phase of extra accelerated expansion at late times, which also produces a higher Hubble constant. And how this is usually done is, instead of making the dark energy density constant over time, you can make it dependent on redshift. So the most common way to do this is WCDM, where the equation of state parameter of dark energy is a free parameter instead of being fixed to -1, as is the case for lambda CDM. And then another model we looked into is PED, which also corresponds to an equation of state parameters smaller than -1. And then if we compare these two methods, then the main difference is that for the early physics, you change both the sound horizon and the Hubble constant. While for the late physics, there's nothing different before recombination, so the sound horizon stays the same, and you only change the Hubble constant. And this is also the reason why these models generally don't work so well. So let's go back to our results, where here I've combined the contours from Shoes and Holy Cow, just to give a visualization of like the most extreme interpretation of the tension. And then let's have a look what happens if we add the early time modifications. Yeah, so here you can see that early dark energy and free NF can move the contours from the CMB more in the direction of the local ones. But it's not really enough. And we cannot shrink the sound horizon more without ruining the temperature and polarization data of the CMB. So this really imposes a limit on how effective these models can be. And then moving on to the late time modifications. Here you see again, because we couldn't change the sound horizon, but only the Hubble constant, that these contours are only moving to the right and not downwards. So this is not a good solution to the combined tension. It may solve H0, but that's only half of the story. Now, in our research, we looked at this combined tension in the sound horizon and the Hubble constant, but there's also other challenges that new physics models will have to address. And one of them is the growth tension. So the tension in sigma 8 omega matter between CMB and large-scale structure measurements. And while the early time modifications were the only sort of promising ones when it came to the sound horizon, it turns out that they introduce a whole new problem when it comes to sigma 8 omega matter. Because these modifications increase the expansion rate in the early universe, which also suppresses the growth of structures. And in order to compensate for that and still preserve a good fit to the CMB data, this means that you have to increase the physical cold dark matter density. So this leads to an increased omega matter H squared and also an increased sigma 8 value, which worsens the tension with the large scale structure. And here in this figure, you can see the gray contours corresponding to large scale structure measurements and the red ones to Planck lambda CDM. And then these model 2 and 3 are models that in an increasing way actually solve the tension in H0 RS, but you see that they introduce a whole new problem when it comes to sigma 8 omega matter. And actually, lately it has been shown that later modifications also suffer from this problem. So I really like to emphasize that we should adopt a holistic approach when it comes to solving the Hubble tension. And this means that new models should not just focus on H0, but also on sound horizon, sigma 8 omega matter, or at the very least, they should not make any of the existing tensions any worse. Which leads me to the main question of my talk. Can modifications of lambda CDM solve the Hubble tension? Well, in my opinion, the answer is no, because there doesn't seem to be one single model that can satisfyingly solve the tension in all the important cosmological parameters. So the early time modifications do improve the tension in H0 and RS, but they worsen the growth tension. And the late time modifications only solve H0 and not RS, and they also worsen the growth tension. So this means that it's extra important to take a critical look at our data points, and also to find some new independent ways to measure the Hubble constant. And that's why for the last part of my talk, I would like to highlight some future perspectives that can hopefully shed some light on the tension problem. And firstly, talking about early time modifications, these are ones that actually leave quite distinct signatures in the small scales of the CMB. And the only reason that we could sort of speculate about these models at all is that Planck doesn't really constrain those small scales so well. So there's some room to play with. But new CMB measurements like the Atacama Cosmology Telescope and the South Pole Telescope are better at constraining these high multiple moments. And therefore they can hopefully distinguish better. So ACT already has 5 data releases, and the results so far are highly disagree highly with an excess of relativistic species. But there's still more data coming from 2019 to 2021. So hopefully within a few years, we will know, we will have data to either confirm or completely discard any of these early time modifications. And then with regards to the local data, there's also many powerful future missions coming up. So one of them is DESI, which you are also involved in. And this will really allow for a great dense sampling of BAO measurements up to high redshifts of 3.5. And this will constrain the combination of H0RS to a sub% level and almost an order of magnitude improvements on the current measurements, which is really great. And another exciting option is that survey telescopes like Rubin Observatory, Roman Space Telescope, and Euclid are estimated to discover many lensed objects. So of the order of 10 to the 5th galaxy-galaxy lenses and 10 to the 3rd quasar-galaxy lenses. And if we look back to this TD Cosmo approach, where they relaxed all the assumptions on the mass profile and are just driven by data, then the current precision was not so good, like about 5%. But with these future forecasts, they're predicted to reach a precision of like 1.5%. So I think this will be a very promising way. But that's not all that they will discover, because besides lensed galaxies and lensed quasars, they're also predicted to discover many gravitationally lensed supernovae, which so far we've only discovered 3 of them, of which only 2 had actually resolved separate images. But the forecasts are that we will get several hundreds a year. And this is why we are also initiating some projects at DARC with Dugas Cody Ramana, Radek Wojtek, and myself, which has as the aim to use these lensed supernovae in cosmology. So the first project we have is to develop a machine learning algorithm that can distinguish between lensed supernovae and normal supernovae in transient surveys. So the idea is to train this model on a large data set of lensed and unlensed supernovae. And then when we give it a new image, it can tell us how likely it is to be a lensed supernova or a normal one. But of course, because we have only discovered 3 lensed supernovae so far, it means that we have to simulate this data set. So here you can see 2 images of unlensed supernovae, where the one on the right is an actual image taken by the Young Supernova Experiment, which is a transient survey carried out at the Pan-STARRS telescope. And the one on the left is simulated with the Lenstronomy software. So this is what we are using to create this data set. Now these 2 are normal supernovae unlensed. So what then would a lensed supernova look like? Well, sometimes you can be lucky and actually see the 2 different images, which of course makes it then easy to distinguish between normal and lensed supernova. But especially with Pan-STARRS, more often the images will not be resolved and it will be more like this. And then you can see that it gets pretty difficult to distinguish between the lensed and the unlensed supernovae. But it's still very important that we can do this, because especially with future surveys like LSST, where we will have terabytes of data coming in every night, it will be crucial to have a fast, automated approach to quickly find the promising candidates for lens supernovae, so that we can then trigger follow-up observations. And then when we have actually a sample of lens supernovae, we would also like to use it for cosmology. So we're also developing a method that can extract the time delays from a time series of images, and then use this to determine the time delay distance and the Hubble constant. And I think this is really an exciting area to work on, because we're in the situation where we have like a handful of objects now, but we know that within a few years, we'll have orders of magnitudes more. And also a difference between lens supernovae and lens quasars is that the time delays are shorter. So it doesn't require us to have like year-long monitoring observations, but it will be in a way easier to get a larger sample with time delays. So with all these exciting future missions coming up, I'm really looking forward to see what we will discover about our universe and how this Hubble tension will unfold. So thank you so much. That was it for me, and I'm happy to answer any questions.
Okay, thank you very much, Nikki, for your excellent talk. And yeah, now we are open for questions. So, okay, please raise your hand. Okay, David was asking a question. So, David, please.
So, firstly, thank you very much for that very nice talk. I have two questions. The first is about the movie. So I think you know which movie I'm referring to, the one that I've never seen, the type of which I've never seen before in a talk. Did you make the movie?
Yes.
How long did that take you?
Yeah, I made it for, we had this online cosmology conference called Cosmology at Home, and we had to record our talk. So yeah, it was sort of fun because you could be a bit more creative. So yeah, I just filmed myself drawing it, which is, I think, I don't know, maybe an hour, and then you just replay it a higher speed.
I'm not sure I ever want to give a talk at a cosmology conference again after this. My second question was about the TD Cosmo data. Could you return, so that you had a slide comparing Holy Cow and TD Cosmo? Sorry, it's quite early on.
No, I have many slides.
Here we go. Okay, so so one thing I'm concerned about here is not the value of the Hubble parameter you're getting out, but the validation of the data. So what does the goodness of fit for these look like? Do they produce like a reasonable do they both produce reasonable chi-squared values?
Oh, I have to say I'm not sure. I think so, but just because the assumptions are very different. So here, if you assume this shape of the mass profile, you will get a good fit and you will get constraints on the Hubble constant. But the problem is that it's not the only option. But yeah, I have to say I don't know exactly about the goodness of fit.
Yeah, I mean, that's my question, right? It's like, are the mass profile assumptions forcing that value while at the same time, like not giving the greatest possible fit, and so giving that tight constraint on the Hubble parameter, whereas the TD Cosmo stuff is a bit more general, which is why you have slightly larger error bars, but at the same time producing a better fit. I was wondering if there's like a way that these could be validated before we then compare them to other. I'm always in favor of validating your data set and checking that your assumptions are valid before you do any kind of like data synthesis, right?
Yeah, no, that's right. That's a good point, actually. Yeah, I'll look into the goodness of fit. Like my thought was just that it's probably a good fit for this mass profile, but it would also be a good fit if you assume a different mass profile, because there's this degeneracy. And then for these lens quasars, we don't have enough velocity dispersion information to really constrain it.
Okay, thank you.
Okay, any other questions? Satoru, please go ahead.
Hi, so such a nice talk. So in the first part, so first you showed some Taylor expansion. So did you use those expansion, or means I think I lost something. Means yeah. So these models were used to fit something. Means
Yeah, we use these to fit the data.
which ranges are those? Means which plots are
Like the redshift range?
okay? And so these models have nothing to do with the H naught RS. So the tension you showed on the H naught RS plane.
Well, all of these models produce contours of H0 RS. And actually, the model that we used for the contours that I show in the end is the second one. So these contours have been derived using model.
Okay. Now I get it. Yeah. Okay. Okay. And in the second part of your lensed unresolved supernovae. So when you train, so what information you feed to the neural network? Means
yeah, we use a convolutional neural network.
Yeah, but what information goes into that? I do not think light curve. So it is just a image on the sky.
Yes. So for the first one where we you do the classification, we feed it a time series of images. So just images, but then on different timestamps.
Okay.
And that's enough to say if it's lensed or not. Then for the other part where we want to determine the Hubble constant, you need a bit more information. So we're sort of experimenting with it now, but we will also probably feed it the redshifts of the lens and the supernova.
Okay, got it. Thank you.
Thanks.
Okay, any more questions?
Yeah, Christoph, let me ask Nikki one question. Nikki, thanks for the talk. So if you follow the work of Subir Sarkar, I'm at the coffee shop, don't worry about the background noise. So Sarkar is saying that there's, if you look at distant quasars, basically the dipole from the quasars is in the same direction as the CMB dipole, but the magnitude differs. And the result is the difference is more or less 5 sigma. Okay, so he's claiming that the universe is not FLRW at a very large scale in some sense. And in a paper earlier this week, we sort of noticed that, you know, when Holly Cow and let's say TD Cosmo, they determine their lenses, I mean, the values vary. And so if you look at the original papers, they sort of, you know, they point out a descending trend of H0 with lens redshift. Right, but it seems that this could instead be a trend of H0 with orientation. So what you'll notice.
I'm just getting the slide for you. This one you mean, right?
Essentially, yeah. But how many lenses you've got? Have you got? Oh, you've got them all. Okay, you've got the Holly Cow lenses here, right? But if you look at the orientations of these, the two highest H0 values are aligned with the CMB dipole, which is essentially the direction that Subir is saying that his quasars, the quasar dipole is also aligned with. So when, in future, when you do get lots and lots of results, or even lens supernovae as well, one can look at the different H0s determined, you know, via this methodology and see whether or not there's any angular dependence.
Yeah, exactly. That will be super interesting because now we see this trend with redshift, but I guess it's not really enough to say something about the trend with position on the sky. Actually, my supervisor Radek was a bit obsessed with this for a little while, and he also looked into it, but he couldn't really find any evidence that this was causing the difference. But yeah, when we have a big sample, if this is the case, then it would be, I guess, more clear to see.
Okay, thank you again. Any more questions? If not, I have a brief question. When you showed this H0 sigma 8 plot, I don't know where exactly it was.
These ones, right?
Yeah. Wouldn't it be better to show F sigma 8 instead of sigma 8? Because F sigma 8 is more what we measure, actually.
Oh, yeah, I don't know, to be honest. I just got this plot from a paper because it illustrates in a nice way how, you know, solving one of these tensions really sort of creates a different tension.
Okay, no problem.
But I guess you would also see it if you plotted with F sigma 8.
Yes, It would be
So-
similar. Yeah.
It depends upon what you're measuring.
Yeah.
Like weak lensing is just S sigma 8, but like redshift space distortion would be what you said, F sigma 8.
So weak lensing shear, this S8 parameter is different from sigma 8. And that's the weak lensing shear measurements.
Okay.
So with RSD, you get F sigma 8.
Yeah.
But
I'm usually doing RSD, so maybe I was a bit
but weak
blindsided.
lensing shear because it's an integrated effect, right? So it's coming from distant sources through the distribution of matter. So it doesn't just measure the amplitude at a particular redshift, right? It's an integrated amplitude. And so this S8 parameter has to include the value of omega matter, which effectively is because of this integrated effect, whereas RSD are very localized.
Okay, thank you. Are there any further questions? We still have some time left, so please go ahead. Okay, in this case, we can thank the speaker again. Thank you, Nikki. It was a great talk. Very good answers to the questions. And then we can stop the recording and
Yeah, thank you so much.
Yeah.
It was really nice also to meet you a bit longer in the beginning. Thanks for
Yeah.
organizing.